A big hello to all the fine students of chemistry out there. This is Dr. David Kreller of the Department of Chemistry, Georgia Southern University. This is my third video in a series of 3 videos about calorimetry. And in this video, we're going to work through a somewhat complicated problem. There will be actually a couple of important steps. It's going to be a multi-step problem. We're going to take a chemical reaction and calculate the change in enthalpy for that reaction. Well, that's no different than what we were doing in the second video, but we're going to take this ability to calculate the change in enthalpy for a reaction and then couple that to the heat flow into a calorimeter, and then from that heat flow predict the final temperature of a calorimeter. So y'all ready? So here is the problem. Now I will let you put the video on pause and give this question, which might seem a little bit wordy, a good read and really figure it out. And if you want, even start trying to solve this problem. Put it on pause, work on it. In terms of the steps involved in this solving this problem, the first step in the sequence is to calculate the change in enthalpy for the reaction. Okay? And we'll do that using the thermochemical equation, which again we learned how to do in the second video in this series. Okay, so that's the logical first step. Then the next step is to predict Q, the heat flow, to or from the calorimeter. Actually, in this case, it's an exothermic process. So this heat flow out of the system and into the calorimeter. To do that calculation, basically using the simple equation that Q is equal to delta H. The heat flow is equal to the change in enthalpy. Okay, so we'll just tie the chemical reaction, the change in enthalpy for the chemical reaction, to the heat flow, Q, going into the calorimeter. So you could say this is kind of our bridge between the reaction and the calorimeter. And then the third step is to calculate T2, final temperature for the calorimeter. Okay. And for that, we'll use this equation that relates the heat flow into or out of the calorimeter to the mass of the calorimeter, the heat capacity of the calorimeter, and the change in temperature of the calorimeter. And remember that this equation has this negative sign because if delta T is positive, and delta T is T2 minus T1, so if delta T is positive, the temperature increased, T2 is greater than T1, right? So if delta T is positive, then the heat flow must be negative, because remember Q is defined with respect to the system. So follow these steps. First step, calculate the change in enthalpy. Well, remember that we're just kind of process we're looking at here. Well, this process is easy in a way because it's all one-to-one stoichiometry. There's no stoichiometry to worry about here. Okay. We're going to turn this quantity of sodium hydroxide that is dissolving in grams into moles. Okay, so we'll do that using the formula weight for sodium hydroxide. Now we've got that in moles, and we'll convert moles of sodium hydroxide into moles of reaction, and again it's just 1-to-1. Right, and then from there just realize that this conversion factor should be upside down. It's flipped over. But anyway, try to imagine that it's correctly correct there. Okay, and then once we've got moles of reaction, we'll convert that to kilojoules of energy. And from there, as we described on the last page, and we sort of made our plan, determine the heat, the Q, the heat flow. Q is equal to delta H. So Q, the heat that flows, is equal to the change in enthalpy. Simple as that. Okay. Now determine the final temperature of the calorimeter. Well, we're told what the initial temperature of the calorimeter is. Okay, so anyway, we'll use this equation, and We'll write this out explicitly that delta T is T2 minus T1. So then we'll put in this value, 15.5 kilojoules, put that in right there for Q, is equal to this. But actually, since this has a negative sign and this has a negative sign, what I've gone and done is like canceled out the negative signs on each side as I've gone to here. Okay. So then, from there, just rearrange that, algebraically rearrange that, and solve for T2. Then plug in the numbers. Thank you for watching this video, and most of all, thank you for working at things, and thank you for learning. It's good for you, it's good for everybody else around you as well. This has been Dr. David Trailer of the Department of Chemistry of Georgia Southern University.